Welcome to another video in the graph series, and finally we are going to get started with some questions today. So this is the first question that we are going to see. Before we move ahead, I would just like to take a moment to remind you to be consistent and make sure you do not miss any videos in the graph series. So make sure you subscribe, hit the notification bell icon. You will also stay motivated and you have no idea how much your support will mean to me. There's so much of free content available on the channel. There's HLD, LLD, DSA, Advanced C++, tutorials, mock interviews, and so much more. So if you think I deserve your support, please subscribe, hit the notification bell icon. And there's obviously a bunch of stuff that I cannot do on YouTube, like mock interviews, live interactive classes. So we have educourses.com. We have live courses, self-paced courses with live doubt solving support, which both of them we have mock interviews, and we have a lot planned in LLD, HLD, Advanced C++, DSA, and so much more. You have no idea. So if you want me to be part of your further learning journey process, please check it out. The link is in the description. And now let's continue. It says find if path exists in a graph. So basically here we are given a source and a destination. So here we are given some edges. We are given integers n. We are given a source and a destination. We have to return a true if there's a valid path from source to destination. What does a valid path mean? So let's look at the examples and let's try to understand what does the question actually mean. In the first example, n is given 3 because there are n vertices. So there are 3 vertices over here, and then there are edges given to us. So 0 to 1, 0 to 1, 1 to 2, and 2 to 0. This is given as bidirectional. What does bidirectional mean? It is same as undirectional graph, or you can see that 0 is connected to 1, 1 is also connected to 0. Similarly, 2 is connected to 1, 1 is also connected to 2. You can go both the ways, right? So this is a bidirectional graph. So here in this example, source given is 0 and the destination is 2. So here actually there are two paths possible. One, there is a direct path from 0 to 2, and there is another path from 0 to 1 to 2. So here, as you can see, we have to return a boolean. So in C++, Java, you can see we have to return a boolean, right? So we will be returning a boolean. Let's look at the second example also. So here you can see this is not a completely connected graph. So here there are two connected components, right? So here the number of vertices are 6 because n is 6. So the numbers are from 0 to n minus 1, 0 to n. Here you can see the numbers are labeled from 0 to n minus 1. So here n was 3, so 0, 1, 2. Here n is 6, so 0, 1, 2, 3, 4, 5. These are the edges. So as you can see, 0, 1, 0, 2, 3, 5, 5, 4, and 4, 3, right? So these are the edges. The source is 0 and destination is 5. Is it possible to go to 5 from 0? So here you can do either BFS or DFS. In both the cases, you will be stuck over here. There is no connection to 5, right? So it is not possible. So this seems like a very simple question, but here we can use our traversals BFS and DFS, and here the edges are given to us, so we have to form the graph. So either we can form the adjacency matrix or adjacency list. So that is why just for this question we will be doing 4 videos, and in this particular video we will be forming an adjacency matrix and we will be doing DFS. In the next video we will do BFS over adjacency matrix, and then we will do BFS and DFS on adjacency list. So in this video we will be doing adjacency matrix and DFS, which is depth first search. First, let's visualize it on an iPad, and then we'll be writing the code in both C++ and Java. So let's get started. I have made both the examples over here. Let's first visualize both of them in an adjacency matrix. So here there are 3 vertices. So my matrix is going to be of what length? It is going to be 3 by 3, right? So order of V square. So 0, 1, 2, 0, 1, 2. And then whatever edges are given to me, I'm going to keep connecting them one by one. Right, and remember that this is bidirectional. So either you can keep the matrix of Boolean or of integer. You can keep of anything. It is not weighted, right? So even Boolean works. So maybe let's start with Boolean itself. So here 0 and 2 are connected. So 0 and 2 is true. Similarly, 2 and 0 should also be true. Similarly, 0, 1. So 0, 1 is true. 1, 0 should also be true. 1, 2 is true. So 1 to 2 should also be true, and 2 to 1 should also be true. So there are no self edges, rest everything is going to be false. So this is how my adjacency matrix is going to look like for this example. Similarly, let's take the other example. Here, what are the number of vertices? Here the number of vertices are 6. So my adjacency matrix is going to be 6 by 6, correct? So here I'm going to take 0, 1, 2, 3, 4, 5. Basically what I am doing over here is going through the edges one by one, right? So in terms of code also you will do that. You can go through the edges in any order, that won't matter. You just have to mark in the adjacency matrix that okay, these all are going to be true, right? Sorry for the shabby diagram, but I hope you understand. Let's start with all the edges. Let's start with this 0 and 1. So 0, 1 is true, 1 0 is also going to be true, 0 2 is true, 2 0 is also going to be true, 3 4 is true, 3 4 is true, 4 3 is also going to be true, 3 5 is true, 3 5 is true, 5 3 is also going to be true, 4 5 is true, 4 5 is true, 5 4 is also going to be true, and rest everything is going to be false. So this is how our adjacency matrix is going to look like, and this is what we are going to use to see whether the neighbors are there or not, and then we are going to do the DFS. In the first example, the source is 0 and the destination is 2. So because we are using DFS, we are going to be taking a stack, and because we are dealing with graphs, what else we are going to use? We are going to use a visited array or visited set or something like that. Let me just take a simple array. So here it is basically 0 1 2. Initially I am marking all of them as false, so none of them are visited. So this is the visited array, right? I'm going to start from the source. Because I'm going to start from the source, I'm going to put it in the stack and I'm going to mark it as visited, right? Because I've already visited it, so I'm going to mark it as visited. Now there are two neighbors, 1 and 2, but because we are doing DFS, we can visit them only one by one. So let's probably start with 1. So now since I visited 1, I'm going to mark it as visited and I'm going to put it in the stack. Who are the neighbors of 1? So there is 0 also, but 0 is visited, so I'm not going to do anything related to that. There is 2 as well, right? So I'm going to mark this as visited and I'm going to put it over here. But now the point over here is that how do I see that who are the neighbors, right? Like, because from the diagram you can easily say ki who are the neighbors. They are basically 0, 1 and 2, right? Who are the neighbors of 1? It's 0 and 2. Basically from the adjacency matrix, what we are going to be doing is that from 0 we are going to see that okay, 0 0 we are going to do nothing, that 0 1, okay, 1 is a neighbor, so we are going to put it in the stack. Then we are going to see that okay, for 1 who are the neighbors? 0, but 0 is already visited, right? So we are not going to visit it again. We are going to see oh, this is false. Then we are going to see oh, 2, so then we are going to put it, right? So you're going to go through the matrix to see who are the neighbors. Let's do properly for this second example. Here also I am taking a stack and I am taking an array visited. So here the vertices are 0, 1, 2, 3, 4, 5. Initially I am going to mark all of them as false because none of them are visited, right? Here my source is 0. So I start from 0. So I put 0 in the stack and I mark it as visited, and then I see who are the neighbors of 0. So I see okay, false. Then there is 1 true. So there is basically 1 is neighbor. So I will mark that as true and I will put it also in the stack, correct? So now that I have marked this, so I come to 1 and I start seeing who are the neighbors of 1. So the neighbor of 1 is 0. Am I going to visit 0 again? Am I going to put it into the stack again? No, because it is already visited. So I'm going to see who else is the neighbor of 1. This is false, 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 false. So there are no more neighbors of 1. So I'm done with 1. So I can actually pop it back, right? So I'm going to remove it from the stack. So I am done with this, right? So now what I'm going to do is I'm going to come back to this and I'm going to see who are the other neighbors of 0. Oh, there is 2 also. So I'm going to put 2 and mark it as visited. Then I'm going to go to 2 and see who are the neighbors of 2. There is 0, but 0 is already visited. Are there any other neighbors of 2? No, because everything else is false. So I'm going to pop it. Basically, I'm done with 2. So now I'm going to come back to 0 and see are there any other neighbors. So everything else is false. So there are essentially no other neighbors. So I can actually pop out 0 as well. So I'm done with the DFS from this source equal to 0. And then I'm going to see is my destination, which was basically 5, is it visited or not? It is not visited. So I can say, oh, this is false. So there is no path, because if there would have been a path, I would have visited it, right? So because this is false, I'm going to return false. Now in DFS, the point that you need to see is that when I move from 0 to 1, now 1 was like my sub problem. Now I need to go to 1 and see who are the neighbors of 1 and deal with it. And because now 1 is the new sub problem, I can use recursion. And basically I'm going to be using the recursive stack. So in the solution, you will not see a stack as such, but recursively, when you draw the recursive stack, you need to have a knowledge about recursive stack to understand this properly. But when you draw it, you will be able to get it properly, because now the sub problem or the current node will become 1 or 2 and like that. And then you will see the neighbors of that. So you're recursively calling the DFS function or your helper function for that particular new node. When you see the code, it will be completely clear. Don't worry about it. Let's finally get started with the code. Firstly, I'll be coding in C++. If you code in Java, you can just go to this timestamp and I will be going through line by line code in both C++ and Java. For Java people, you can go to this timestamp. For C++ people, you can just continue. Before actually doing the traversal, the first thing that we have to do is form our graph. So here we can see we are given n and we are given edges. So we have to form the graph. How will our graph look? It is basically a 2D matrix of n by n, right? So I can basically make a vector of vector. Again, I could make this of either Boolean or of integer. Right now I'm making it of Boolean and I'm going to call it adjacency matrix or whatever you want to call it. You can also call it graph. Let's call it graph and we can make it n by n, right? So vector of again Boolean and again the number of columns is n and I am initializing the whole thing by false. So initially the entire 2D matrix is false. Now what I am going to do is that these edges are given to me, right? 0, 1, 1, 2, 2, 0. I am going to go through each of these edges. So basically for every edge in this edges, so if you note over here, this is a vector of integers, right? So vector of integers. So each edge is basically a vector of integers. So this is one edge and this entire thing is edges, right? So there are two values u and v. So basically this is like the starting point and this is the ending point of the edge like that, right? So u and v. So for that what I need to do is, so basically if you see like this, so there are two values, edge of 0 and v is edge of 1. You don't need to create u and v. I'm just writing it like this for further clarity so that it becomes easier for you to visualize it. And now what I'm going to do is graph of uv is going to be true and similarly graph of VU is going to be true. Now a lot of people miss this line that graph of VU should also be true and that is why you should see that it is a bidirectional graph and if you are in an interview you should be asking these questions, is it a bidirectional graph or is it a directed graph, and based on this you will be making a adjacency matrix or adjacency list, right? So you have done this, instead of u and v you could just write edge of 0, edge of 1, edge of 1, edge of 0 like that. I've written it like this for further clarity. So now we are done forming the adjacency matrix and now we will be doing our DFS. But for DFS we need one more thing. What is it? Our visited array. What will be the size of our visited array? That will also be of the size n, correct? And also initially I will mark all of them as false only. So again it will be Boolean only, so vector of bool and I'm going to call it visited. The entire thing will be of length n and I'm marking it as false. And now we are ready to do DFS. So now we'll be writing a recursive function for DFS. Now you can call this literally anything. You can call it DFS, you can call it helper, you can call it valid path helper or literally anything right now. So let's call it DFS, okay? And what I'll be doing is I'll be calling the DFS and I'll be passing the graph. What else do I need to pass? I obviously need to pass the source, the destination that is given to me. I need to pass the visited array that we have made. What else do I need to pass? Probably n, correct? Now let's try writing the helper function or the DFS function, and inside this I'm going to pass the graph, right? So this is how my graph looks. It's a vector of Boolean, and remember while passing all of this we can just pass by reference because we don't want to create the copies again and again. This is something that you should keep in practice for C++. And then we are passing source. I'm calling it src and I'm calling destination, and then we are passing int n. Correct? Now the question is that what should I be returning from here, because I have to return a Boolean, right, if there's a valid path or not. So I will actually get the answer from DFS itself. So I can just return the answer from here and I should be returning a Boolean from here. So if there is a valid path, I should be returning true. Otherwise, in the end, I should be returning false. So in the end, if I do not find a path, I will be returning false. Or if I find a path, I will be returning true. Cool. So in DFS, what is the first thing that we have to do is that we have to go to all the neighbors of this particular source, right? So how do I go through all the neighbors? So I have this adjacency matrix, and what am I going to do is I'm going to check the entire row, right? Entire row. So for int I equal to 0, and what will be the length of the row? It will be n because it is n by n matrix, right? So I plus plus, and which row am I checking? Which row am I checking? I am checking the graph of source, the source wala row, and I am checking I. So if it is true, that means the source and I are connected. If it is true, and what else do I have to make sure? I have to make sure that I is not visited. Otherwise, I'll keep calling the same thing again and again, or I'll end up in a forever loop. So this says that I is my neighbor, only then graph would have been true. And here I'm checking that I have not visited that neighbor I, correct? So now I have a neighbor which is not been visited. So now what I'm going to do is I'm going to call the DFS again for the same graph, but now what is my source? Now my sub problem is that this new neighbor is my source now. So I becomes my source, the destination is still the same, and the n is also the same. So now where will I stop this recursion? Now what all places can I stop the recursion? One place is that whenever I have the source itself as the destination, I can say that yeah, I have found the answer, I can return true, right? Because I will keep recursively calling it, and with every recursion call I can check that whatever this DFS function is returning, if it is true, I can just return true, otherwise I will return false. And that is it, we are done. There is just one thing remaining, and think about it. I hope you are able to come up with it yourself. Here I have checked that I should not be visited. But every time I am visiting a node, I also have to mark it as visited. So every time you're dealing with visited array or set or map, you have to check these two things. One is that you're marking it as visited, and second thing is while calling it, you are checking it as visited or not. So here every time I start going to the neighbors, before that I have to mark it as visited. So I mark visited of source as true. So if source word is confusing you, you could also say it as current. So you can say if current is your destination, visitor of current is true. Maybe that will make it clear ki graph current, like who are the neighbors of that current, I is there or not. So you could also call this source as current and you can deal with it. Now let's try running it and see if it works or not. Okay, so I forgot to pass this visited, and let me just do that. Okay, so I am passing this, and here I am again passing it as reference. So make sure you always pass your vectors and everything by reference in C++. Let's try running it now. So yes, we have passed all the cases, and let's submit it. So here you saw that we got time limit exceeded. Why did we get? Can you guess about it? So we passed all the cases, but we are getting time limit exceeded because we have used an adjacency matrix instead of adjacency list. So yes, that we had discussed about this in the initial videos, that we should be using adjacency list because there can be a lot of zeros or a lot of false in the adjacency matrix. Basically, we are using a lot more space and we are going through it again and again, right? So adjacency list is actually more efficient when we have sparse graphs. Remember, we had talked about it, and there's a possibility that there are a lot of sparse graphs, but it is important to understand these things, and actually you should be able to do the DFS on adjacency matrix. Also, you should be used to writing both the adjacency matrix and adjacency list. That is why in the next video we will be doing BFS on adjacency matrix as well. So please show up. Before you go, let's quickly look at the time and the space complexity. So here first we have formed the graph, right? So our graph took how much space? Order of v square, and we took order of e time complexity to fill in the edges also, right? To fill in the matrix. So order of v square is the space that we took. What else space that we need? We needed the space for the visited array, so that was another order of v. Also, if someone asks you what is the space for the recursive stack, so in the worst case, how many calls will you be making? Think of it like a proper stack. In the worst case, how many nodes will you be putting in the stack? It will be order of v, right? So recursive stack also using order of v. For the visited array, you are using order of v, and for the graph, you are using order of v square. Now that is the space complexity. Now let's talk about the time complexity. So here again, okay, order of e to put in the graph and all of that is there. But for DFS, like in the worst case, but for DFS, what is the time complexity you took? So in very simple terms, think of it like this. In the worst case, you'll be visiting every element of the adjacency matrix exactly once. Correct? Because you are not going to visit the same nodes again and again. You're going to check the neighbors once, right? So order of v square is the worst case time complexity for DFS. Actually, it is the same for DFS and PFS. You will see it in the next video as well. And now for the Java people, I'm going to write the code again in Java. So the first thing that we have to do is form the adjacency matrix, and what will be the size of it? It will be n by n, and again we can make it of Boolean or of integer. So right now let's make it of Boolean, and we are going to call it as graph. You can call it as anything. You can call it as adjacency matrix. You can call it literally anything. So it's a 2D matrix, and I'm going to call it graph, and I'm going to do new Boolean, and n by n will be the size of it, right? And initially what I need to do is I need to mark the entire thing as false because initially they're not connected, and then we are going to go through all the edges and then mark them as true for all the edges, right? For both the directions. So I'm going to go through all the rows one by one. So row in this graph, and I'm going to fill the entire thing as false. So now we are given the edges and we have to go through the edges. So this is a 2D matrix that is given to us. So this is the 2D matrix, and here each row is basically an edge, right? So 0, 1. So 0 and 1 are getting connected. So we have to go through each edge one by one. So how are we going to do that? There is going to be another for loop. So for each edge in these edges, so basically each edge will be the 0, 1, 1, 2, 2, 0. We will have two values, right? So there is one edge of 0 and there is one edge of 1. So you actually don't need to write this u and v. I'm just writing it so that it is easier for you to understand. So what I need to do is graph of uv, I'm going to mark it as true. And yes, this is what a lot of people missed, that they will not mark graph of vu as true. You need to do this also because it is bidirectional, and in interviews you need to ask these questions to your interviewer. That is it bidirectional, should I be marking graph of vu also as true or not. So here we have marked both graph of uv as true and graph of vu as true because it is bidirectional. And you could write the code as edge of 0, edge of 1, edge of 1, edge of 0 also. Here I have just written like this for further clarity. So now we have formed the adjacency matrix, and now we can start doing the DFS calls. But before that, what do we need? We are dealing with graphs, so we need a visited array, right? So again, that is going to be also a boolean. So I am going to call it viz, and I am going to create a new boolean. And again, what will be the length of this? It will be n only. So now I am going to call the DFS function. And what all things do I need to pass? I need to pass the graph, and I need to pass the source that is given to us and the destination that is given to us, and I'm going to pass the n. Now you could be calling this DFS function as anything. You could be calling it helper, you could be calling it valid path helper, you could be calling it anything in the whole world. I'm just calling it DFS for further clarity. And also, what should be the return type of this DFS? So here, if you see, here we are supposed to return a boolean, right? So this DFS should also be returning a boolean because it is supposed to return as an answer. So whatever function we are going to write, we are going to make it as boolean. The return type is boolean, and we are going to return the answer from here itself. So let's write this DFS function now. I'm going to keep it private itself. So private, and the return type is boolean, and I'm calling it DFS, and I am passing the graph. How does our graph look? It's a 2D boolean array, right? So I'm going to pass the graph, the source. So I'm calling it src, the destination, and the n value. And I also need to pass the visited, right? So without that, otherwise how are you going to mark it as visited, right? So I am also passing visited, and here I need boolean. So this is supposed to be returning a boolean. So if I get the destination at any time, I'm supposed to return true, otherwise I'm going to be returning false, correct? And what do I do in DFS? I basically go to all the neighbors of this source, and then that neighbor is going to become my new subproblem. I'm going to do DFS again from there. So first thing that I need to do is I need to go through all the neighbors and see are they visited or not. To go through all the neighbors, I need to go through the entire row. What will be the length of the row? It will be n only, right? So if for int I equal to 0, I is less than n, I plus plus, I need to go through the entire row, and the row will be, which row do I have to go through it? I am checking graph of source and I. So basically for graph of source, I am checking all the I values. You could also call this source as current because this is my current node, and I am checking all the I's, basically the entire row. Is it true or not? If it is true, then that means it is a neighbor. So if this is true, that means source and I are neighbors. They are connected by an edge. And now I also need to make sure that this has not already been visited. This I has not been visited, right? So I need to be sure that this is not visited, and only then if it is visited, if it is not visited, what am I going to do is I'm going to call the DFS again. I'm going to pass the graph, but now my new source is going to be this neighbor I. The destination is going to remain same, the visited and the I and the n. So basically what I'm doing is I am now to a new subproblem. Now my I will become my current node or my source node, and from this I will start checking key is there a path to destination or not, because this is one possible neighbor. Like this, I am through the for loops, I'll be considering all the neighbors. I'm going depth wise. So first I am considering the depth where I is my neighbor, and then I'm checking. Where am I going to stop all of this? At any point, if I find the destination, so basically if my source becomes equal to destination, I am going to return true. So similarly over here, when I call the DFS function, I will be getting something in return, right? Because this is Boolean. So at any point, if I get true, that means I have found a path to destination. I am going to return true. Otherwise, I am going to return false in the end. Now, there is just one last thing that I hope you are also thinking yourself, that here I am checking key is it visited or not, but I have never marked it as visited. So whenever you're dealing with visited array or set or map, you always have to be sure that firstly you're checking that it is visited or not. Second, you also have to mark it as visited, right? So before going through the neighbors, I am marking the source as visited. And also here you could call this as current. Again, saying this again for simpler understanding, you could call this as current. So if current is equal to destination, you would return true, and you would mark current as visited, and you would go through all the neighbors of current. So that might be easier to understand. But yes, we are done, and let's run and see whether this works or not. So this works, but now let's submit it. So on submission, we got memory limit exceeded. Why is that? Because like we had learned this in the starting few videos, that in adjacency matrix for sparse graph, we are going to end up taking a lot of space, and that is what is happening over here. So adjacency list would be a better approach, and that is what we are going to do. But it is important to understand BFS, DFS, and you should be able to write code of both BFS, DFS on adjacency matrix as well. Before you go, let's quickly look at the time and the space complexity. So let's discuss the space complexity first. For the graph itself, for the adjacency matrix, we take order of v square, and we have filled it also, right? Order of v square, so time complexity is also there. Then another order of e time complexity also to fill in the edges, because you're going through all the edges. So talking about the space complexity, order of v square for the graph, order of v for the visited array. What else space are we taking? So think about the recursive stack as well. If you think about the actual stack, in the worst case, how many nodes are going to be there in the stack? Order of v, right? So here we are using the recursive stack space also, which is again order of v. So your total space complexity is order of v square for the adjacency matrix, order of v for the visited array, and another order of v for the recursive stack. Now let's talk about the time complexity. Other than order of v square for the graph and order of e in filling the graph, let's talk about the DFS. How much time complexity does DFS take? Now think of it in very simple terms. In the worst case, we'll be visiting each element in the adjacency matrix exactly once, right? Because we are not going to be visiting the same node again and again. So in the worst case, the time complexity is again order of v square. That is true for both DFS and BFS, and you will see it in the next video as well. In the next video, we'll be doing BFS on the adjacency matrix, but after that, we'll deal with adjacency list as well. All of this code is extremely important. I cannot emphasize it enough, and I hope you are understanding line by line. If there are any questions, let me know in the comments. It is extremely important, and I hope you're going to watch the entire series and you're going to become an expert in graphs. If you like all the hard work that I'm putting in, I'm putting a lot of free content now. Like I do have courses and EduCourses, but I love to put on free content as well, and I would love to help you out in any way possible. If you're liking my work, please do subscribe, please do hit the notification bell icon. You have no idea how much it will mean to me. There are so many people who have not subscribed. You have no idea how much it would motivate me to create more. If you could just subscribe, and also check out EduCourses. The link is in the description, and see you next time.